Welcome to another chapter in the photovoltaics module. In this third chapter we will deal with solar cells and modules made of crystalline silicon. This learning unit deals with the production of silicon wafers. Silicon solar cells have already been discussed more frequently in chapters 1 and 2. You may wonder why silicon plays such a big role for photovoltaics. The first reason is that silicon is the most abundant semiconductor material on Earth. After oxygen, it is the second most abundant material in the Earth's crust, so it is plentiful. Another reason is the bandgap of silicon, which allows for a very high theoretical efficiency. Both have led to silicon-based photovoltaics having a market share of over 90% today. The technology is mature and the industrial processes are very efficient, which means that production costs are low. In this learning unit, we'll talk about the production processes of silicon wafers. Because of the high energy demand, these processes have a major impact on the energy payback time of solar modules. That is, the time it takes a finished solar module to produce the energy that was needed to make it. Let's first get an overview of the production steps. First, polysilicon is extracted from the quartzite. The polysilicon is the starting material for the production of mono and multicrystalline ingots. The ingots are cut into wafers and then further processed into solar cells. Finally, the finished solar cells are assembled into solar modules. In this teaching unit, we will deal with the first three process steps. The starting material for the production of polysilicon is sand. Theoretically, any sand could be used for this purpose, but normal sand also contains many other substances. Therefore, quartz or quartz sand, which consists of silicon dioxide, is usually used. In this first step, this quartz sand, the silicon dioxide, is deoxygenated. To do this, it is mixed with coal or another carbon source and melted in an electrical arc furnace at a temperature of 2000 degrees Celsius. The applied heat causes the oxygen to separate from silicon and form carbon monoxide with the carbon. The molten silicon is cast into beds to solidify. This metallurgical silicon has a purity of almost 99%. That means it contains 1% elements other than silicon. Even though this sounds very pure, it is not sufficient for the production of solar cells. This is because the foreign atoms introduce numerous additional energy levels in the silicon crystal. This is similar to doping, where foreign atoms are specifically introduced into the crystal. In a sense, the polysilicon is both heavily p and n doped. Because of the many energy levels, the recombination rate increases and it is not possible to create a p-n junction. For use in a solar cell, there must be no more than one impurity atom for every 100 million silicon atoms. In other words, we need a purity of 99.999999%. This means that the silicon has to be cleaned and other elements have to be taken out. Since it is very difficult to purify the silicon in its solid state, a chemical process is used. In this process, the silicon reacts with hydrogen chloride in a reactor to form trichlorosilane. The trichlorosilane, which is liquid at room temperature, is then purified further and further by repeated distillation. The silicon must then be separated from the hydrogen chloride again. The so-called Siemens process is usually used for this. The purified trichlorosilane is introduced together with hydrogen into a reactor, where it is heated to over 1000 degrees Celsius. The reactor contains two heated thin silicon rods. From the trichlorosilane, Now gradually silicon deposits on the rods, which grow in this way to form thicker rods of polysilicon. In these polysilicon rods, there is at most 1 foreign atom for every 1 billion silicon atoms. The purity of the silicon is now sufficient for use in solar cells. To understand the next process step, let's first look at the crystal structure of a silicon crystal. In the ideal case, we have a single crystal, that is to say, a crystal with perfect crystalline order. Each silicon atom in this crystal has exactly 4 bonding partners. The polysilicon, however, does not consist of a single crystal, but of many small single crystals. The boundaries between the single crystals are called grain boundaries. At these grain boundaries, not all silicon's atoms find a bonding partner. This results in electron traps. Remember what we learned about surface recombination. Just as in a surface, these boundaries lead to an increased recombination rate in polycrystalline silicon compared to single crystals. In order to reduce the recombination probability in silicon, the crystalline structure of the silicon is therefore changed in the next process step. The standard process for the production of monocrystalline silicon is the so-called Czochralski process. For this, the polysilicon rods are broken and melted in a crucible. At this point, doping atoms are added to the silicon. In the past, boron was used for this purpose, but today gallium is mostly used for p-doping. A seed, a small single crystal, is then immersed in the melt. Subsequently, the single crystal is slowly pulled up again under slight rotation, and in the process, silicon continuously crystallizes at the silicon seed and cools down. Within several days, a silicon single crystal of up to 2 meter length is formed. Prior to the next process step, the ends of the cylindrical ingots are cut off from this silicon single crystal. They can be reused for the next melt. In addition, the ingot is cut to a pseudo-square form. Although this means that some of the valuable monocrystalline silicon is lost, the surface area in a solar module is better utilized later than with round wafers. Before we now turn to the next process step, cutting the wafers, I would like to discuss another way of manufacturing silicon crystals. We have learned that monocrystalline silicon achieves the highest efficiencies in silicon solar cells. However, the manufacturing process is very complex and the wafers are therefore expensive. It is comparatively easy to produce multicrystalline wafers using the ingot casting process. As in Czochralski process, the polysilicon rods are broken and melted in a crucible. The crucible is then allowed to cool from the bottom. On the bottom of the crucible, small single crystals form in various places, which continue to grow sideways until they touch. The crucible is then allowed to cool from the bottom to the top. This can be achieved, for example, by slowly pulling the heating rings upwards. This special cooling technique causes the crystals to grow upwards like columns. This is advantageous because later the charge carriers do not have to cross any crystal boundaries in the vertical direction that way. After the silicon block has cooled, it can be released from the crucible. The individual single crystals can now be clearly seen on the surface of the block. The very large silicon blocks are then sawn into smaller blocks. These blocks can now be cut into wafers in the next step. The finished silicon blocks are now cut into wafers. In recent years, diamond wire sawing has become the standard for cutting wafers. Here, a diamond-studded wire is guided over the silicon block by guided rollers and simultaneously cuts out many thin slices, the wafers. The sawing losses that occur here depend primarily on the thickness of the wire. Wire diameters of around 60 micrometers and wafer thicknesses of 180 micrometers are common. For comparison, a sheet of paper is 120 micrometers thick. The finished wafers clearly show the starting material. Wafers made of monocrystalline silicon have a so-called pseudo-square shape and a uniform surface. Wafers made of multicrystalline silicon can be recognized by their square shape and the irregular surface on which the individual crystals are visible. The sawn wafers then undergo a chemical bath to repair thawing damage. After this, the wafers are ready for processing into solar cells. We'll deal with this in the next lecture. Let us summarize this learning unit. First, raw silicon is obtained from quartz sand, which still contains a lot of impurities. By purifying the raw silicon and subsequent Siemens process, one obtains rods of polycrystalline silicon with high purity. These silicon rods are melted down in the next step and used either to produce monocrystalline ingots or multicrystalline ingots. Finally, the finished ingots are cut into wafers. And in the next learning unit, we will look at how solar cells are made from the wafers. Thank you for your attention.